Hello everyone. So today we'll be learning something new here. So what happens is you should understand a few things when it comes to earthquake viewpoint. What happens is when it comes to a structure, there is something called as irregular and regular structures. So right now in this session, I'll be explaining you guys about the regular structures. Normally what happens is imagine you take a book or something like that and you try holding it on your fingers. So tip of your finger. So what happens is if you're trying to hold it, if you hold it at the side or something, and it is quite difficult holding it. But if you are going with the center of the book, you will be able to hold the book easily. So that is called as the average position of all mass within an object. So what happens? All the masses in the book that is accumulated is at the center. The same way, there's something called as center of mass. So in a building, when a center of mass is defined, that means there is something called as that is accumulated here. The mass is accumulated here. It is primarily affected by the distribution of the weight within an object. So that is how center of mass works. Then there is something called as center of stiffness or center of rigidity. So what happens is a structure will have its own capability of resistance. So normally what happens if there is a slab in here, there's a slab in here and there is a column in here. There's somewhere a center of stiffness in this, maybe here or something like that. So example, center of mass is here, center of structure is here. So center of structure represents a point where the lateral force can be applied without causing rotation. So what happens is whenever a load is acting, a load is acting, earthquake load, wind load or something like that, there are three things that is going to happen. The first thing is the load, because due to the load, the building will move like this. The first thing is like this. Then there is something called as one is like this due to the load by this side. The other one may be like this, it will go out like this. Then there is something called as a torsional movement, that is this. So there are three ways. So one is this. This is the first one. This is the second one. Then there is a third one. This is a rotational force, and this is a very dangerous thing. And we should be very careful with this rotational thing. That is the reason that why we need to learn about the center of mass and center of stiffness in a horizontal regular building and vertical irregular building and horizontal irregular building. There are three things in it. So now example, imagine at the beginning, like what happens is there is a torsion. So due to the load acting, there is a torsion happening, and if it happens at the beginning, that is called as inherent torsion. Okay. Then what happens is, example, imagine if I'm applying a load like here or something like that. If I'm adding some kind of a load, maybe example, if I'm adding some kind of a machine load or something like that. If I'm adding here something like that, what happens is there's some kind of an additional load, right? Additional load happening, like added. So what happens? The center of stiffness, if it was here, it will come here, and it won't be equal to this. So center of mass and center of stiffness won't be equal. And if that is not equal, it is a big problem when it comes to a irregularity. So what happens? It happens like, I'm sorry, not irregularity. It is like the torsion happens due to that. If COS is not equal to COM, that is center of mass is not equal to center of stiffness, then there is a possibility of torsion. And you should be very careful whenever you design a building. You should make sure that the center of mass is equal to center of stiffness. A few like percentage reduction or something like that can be taken, but you should be very careful. It should be coming within a limit. So this is how it works. So if you guys have understood how this is, next will be I'll be explaining is what are the types there, all those things. So what happens now, as I've explained you guys, what is torsion right now. So irregularity torsion. So irregularity building. See, definition of irregularity building. Plan irregularity. Plan means horizontal. That means right now whatever I explained you guys, right? Whatever you guys see here, like this is this structure is there. No, this is plan. This is horizontal, and vertical is something like you take a building like this. This is vertical. So this is how it is. For right now, we are going with the plan irregularity. So I have explained you guys what is a torsion irregularity right now. So whatever the definitions are there, that is given in here. Then what happens? There is something called as due to the load acting. Correct. Due to the load acting, there is a movement like this. There is a sway like this from this position to this position, and that is called as delta minimum and delta maximum. What happens is whatever the delta maximum is there, no, if it is more than 1.5 minimum, 1.5 minimum, then there is something called as torsion irregularity. So that is the reason they have given here in the range of 1.2 average to 1.4 average, in which the horizontal minimum is the delta minimum is the horizontal total displacement, which is smaller in amplitude at one end. The building configuration shall be revised to ensure that the natural period of the fundamental torsional mode of oscillation shall be smaller than those of the first two translation modes. That means whatever the translation mode is there, no, this one and this one and this one, there are three translation modes. So according to the natural period it should go, and torsional mode of oscillation shall be smaller than those of the first two translation modes. That means whatever the torsion is happening, no, that should be lesser than this one and this one. So you should be very careful on that along the principal plan directions. Then three-dimensional dynamic analysis should be done. So we should follow the dynamic analysis method in this case. If more than 1.4 delta, if what happens if the delta whatever we get here, no, if this is the range, then it's fine. If it is crossing that average this thing delta, then what happens is we need to revise the building. So we should be very careful on this one. So please work on this. Whenever you are designing any building, you should make sure that the torsional moment, whatever is happening, it should be below 1.2 to 1. Like between 1.2 delta to 1.4 delta. So what is delta average? That is delta max plus delta minimum, right? 2. So this is how it works. Next is re-entrant corners. So what happens is there are corners where you should be very careful about. Example, what happens in this case, the length, whatever you see, this length and this length, when you compare a by l, whatever the length is there, if you divide by this one, what you get, it should be like it should be more, it shouldn't be more than 0.15. So what happens? A building is said to be re-entrant corners in any plan direction when its structural configuration in plan has a projection of size greater than 15%, and we should be very careful that it shouldn't be more than 0.15%. So we should be very careful on that. In a building with re-entrant corners, three-dimensional dynamic analysis method should be with flexible flow diaphragm shall be adapted to capture the concentration of forces generated in the reentrant corners, especially in the floor diaphragm. See, I have explained that these things in the last video. You guys can check that out about the diaphragm, where I have explained you guys about the floor diaphragm and the rigid diaphragm. Here they have explained the same. So to capture the concentration of forces generated in reentrant corners, especially in the floor diaphragm, so we need to use flexible floor diaphragm. And when special elements adjoining reentrant corners, this is an addition to the case of rigid diaphragm analysis. It is applicable on the worst effect consideration. See, what happens normally is whenever there is a structure, we always go with the rigid diaphragms because we use concrete slabs. So that is normally a rigid diaphragm. So in a building with re-entering corners, three-dimensional dynamic method with flexible should be adapted. That is what they are trying to tell. If you are going to use this method, like if there is a re-entrant corners, we can use that. But normally what happens is we should be very careful. We shouldn't give a re-entrant corners. Okay, hope so you guys have understood this one now. So a reinforcement corner, especially in the floor diaphragm, and is a special element joining reinforcement corners. This is in addition to the case of rigid diaphragm analysis. Okay, as you guys are doing rigid diaphragm analysis, again you need to do for the flexible floor diaphragm also. Like you should do the analysis for that also for three-dimensional dynamic analysis, like by using this. Okay, so three-dimensional dynamic analysis method should be followed with flexible flow diagram, including rigid diaphragm analysis. Okay. Now, floors with having excessive cutouts. What happens? Some of the people, what they do is they give a lot of space in there. Okay, so we think it's kind of cool or something like that. It is kind of good looking or something like that. But we should be very careful. There are a lot of things that are coming to a factor when it comes to a building. So if it is more than 0.5 into a total, that means the total area is there. No, if you multiply that with 0.5, if it is more than if this one is more than this like whatever we have calculated, it's very dangerous. It's not good for the building. So we should be very careful whenever we are designing some building. We should be less than always less than 0.5 into 8 total. I mean the cutout, whatever is provided. So opening in slab results in flexible diaphragm behavior. See, flexible diaphragm is bad for the building, and hence lateral shear force is not shared by the frames or vertical members in the proportion to the lateral translation stiffness. The problem is particularly accentuated when the opening is close to the edge of the slab. A building is said to have discontinuity in planes when the floor have cutouts. See, that is what I've explained you. In a building with floor slabs having excessive cutouts, so if the geometry is less than this 50%, the floor slab shall be taken as rigid or flexible in plane in structural analysis of a building depending on the location and the size. Okay. So if it is like less than 50%, it's fine. We can take it as rigid or flexible. We'll go with rigid itself. Okay. More than 50%, the floor shall be taken as flexible in plane, and the movement will be more in that case. So you should be careful on that. Next is vertical elements. What happens is there is a vertical element here. You guys can see here. What happens? uh, as you guys can see here, there is a vertical element in this, and it is coming out, the projection is there. So usually what happens, we should be very careful. We shouldn't give this kind of a projections. If it is given, what should be done? See, when it comes to a special see sorry, yeah, specialty literature shall be referred to for the design of such buildings. If the building is located in zone 2, okay, if zone 2 is the location, we need to go with the special literature. If the zone is 3, 4, 5, the forces and the moment due to the earthquake effect in the elements connecting the two vertical elements with the out of plane offset elements, the vertical element supporting the offset and the connection shall be enhanced by the factor of 2.5. So what happens is the forces and the moments whatever we are calculating, no, like example, if the moment is around 50, we should go with at least 2.5 factor, something like that. We need to overestimate, and we need to calculate the forces, something like that. So that is how it works. So next is lateral drift. So what happens is lateral drift is something like that. If a building is there, there will be a drift like this due to the load acting. So we should be very careful on that. Lateral drift shall be less than 0.2% in a story having the offset. So example, what happens here, the story is offset like this, no, this area, it should be, the drift shall be less than 0.2% in the story having the offset. So wherever there is an offset, it should be less than 0.2% the drift. So if you're very careful on that basis. Okay. Next comes the non-parallel lateral force system. Building undergoes a complex earthquake behavior. Hence, what happens is whenever there is a load acting, a lateral force acting, there is a two plan direction. See, you guys can see this, no? Whatever the plan is there, we provide this shear walls. Okay, once we provide the shear walls, there will be a rigidity formed, and the center of stiffness changes, and the center of mass also changes. So what happens in a building with non-parallel lateral force resisting system, non-parallel resisting building shall be analyzed with a combination of 6.3.2 and 6.4.1. So what happens, 6.2.2 is giving this these clauses. So normally what happens, a building is said to have non-parallel system when the vertical oriented system resisting lateral forces are not oriented along the two principal orthogonal axes in the plan. So orthogonal plans is like the plan is this one. This is the plan. Okay, and when a vertical oriented structure resisting lateral forces are not oriented along the two principal. See, if this is not happening, okay, this is not happening. What happens? So here they are saying that if the behavior like lateral force resisting oriented to plan direction are orthogonal to each other, that is fine. A building is said to have non-parallel system when the vertically oriented structural system resisting lateral forces are not oriented along the two principal orthogonal axes. If it is not oriented like this, then this is a non-parallel lateral force. In that case, we are going to follow these two methods. So we need to go with this one of this clause where they are saying that ELX plus or minus 0 ELY should be followed. ELX means this one, ELFY means this one. Whatever we have seen at the first video, no? So this one, whatever, 1 and 2, like X and Y. So this is how it works. Now, 30% should be taken into consideration. That is the reason 0.3 is taken. Okay, when the lateral load resisting are not oriented along mutually orthogonal horizontal direction, structural shall be designed for the simultaneous effector due to the full design of earthquake. Okay, thus the structure shall be designed for the following set. So that means ELX plus 0.3 ELY, then ELX minus 0.3 ELY. So this is how it works. Okay, are two orthogonal horizontal plane. Okay. Then comes when lateral load resisting elements are not oriented along the mutually orthogonal direction, structure shall be designed for simultaneous effector due to the full design earthquake. That is this. Okay. Then thus EL load combination given in 3.1 shall be replaced by whatever the load here is there. No, see, this one is the extra thing that is coming. So what happened in 3.1? We have to like 6.3.1. We had to replace this one by the given load combination. So that is how it works. So ELX is given ELY, see, 1.2 DL IL plus or minus EL 0.3 L by 0.LZ. So this is for what? See, there are three things in this: LX, LY, LZ. You should understand that. So XY orthogonal plane and vertical direction. When there is a vertical direction acting, so as usual, as I've told you guys, X, Y, and Z. There's one more axis. Three axis if it is acting, then we go with this one. We follow this method. Okay. So what happens? This implies that the sets of combination, load combination involve earthquake effect considering these things. Okay. So if there are three things, when response from three earthquake components are considered, the response due to each component may be combined using the assumptions that when the maximum response from one component is 30% of the maximum of all of them. So that means this one. So you can see three of them, right? LX, LY, LZ. Here what is it? LX and LY. That's it. Only two of them. LX and LY. Here there are LX, LY and LZ. There are three things. So these are the difference when it comes to a normal bending. Like this is where it is orthogonally horizontal member, but we are not taking the vertical thing, but here we are going with the vertical too. So that is the reason they have mentioned here. They are going to use the vertical member. Like if there is a load acting on the vertical member, then we are going to consider this. So this is how it works. Yeah. So 1.2, whatever you guys can see here, no, this is the last answer that you can get. So here, whatever was there, they have applied it here. Okay. Hoping so you guys have understood this. If you like the video, please do like, share, and subscribe. For more videos, please do subscribe, press the bell icon. Thank you.